Got it. Yes. Um, Sorry. I'm forgetting how I actually, there we go. It's over here. This little button is hidden. Wonderful. Yes. I'm excited to talk to you all today about some aligned in my work, which is specifically about thinking about ideas from game theory and online learning to talk about human and AI collaboration. So, as I give this talk, I just want to say that one of the co-authors on this work really tragically passed away recently. So I just want to make sure to honor her at the start of this talk. Emily Ryu, she was a really wonderful researcher, a wonderful friend, and she brought a lot of joy to everything she did. That included research. And I hope that you can see some of that joy in the talk I give today. Um, and then, of course, I have also some other wonderful co-authors. Um, Varun, Ira, Myra, Serbi, and Aaron are all on at least one of the papers that I'm going to touch on today. So the general motivation for this line of work is that increasingly humans are using AI to help make decisions. So the motivating through line we'll see in this talk is we have a doctor and we have a AI system. And say a patient comes in and this patient would like to get help. And the doctor would like to come up with a good medical solution for them. Um, and that there's some information that is about this patient, which is perhaps immediately legible to the doctor and also to the AI system, something that they read on their intake form, so that they can both kind of directly understand the implications of. But on the other hand, there's some information this AI system has. It's able to aggregate information about other patients and see patterns in ways the doctor might not be able to see. And on the other hand, even if this is a super powered AI system, there will always be some things a doctor can see. They're there in the room with the patient. You know, they can see how they're feeling at the time, what they're looking like now, how they react to pain. So both of these systems have their own expertise that we would like to be able to combine in a useful way. Um, and I see two natural concerns with this interaction. The first is alignment. So, how can we be sure that the AI is optimizing the same thing as us when we ask it for help in coming up with recommendations for the treatment plan for this patient? And the second is complementarity. Even if it is perfectly aligned, how can we best integrate its output, which might be using insight on information that we don't have, but we have some other information? How can we best integrate that with our knowledge? So these are the two things we're going to focus on today. And we're going to start with the second question. Let's start with, okay, what if they are aligned? Because it's already a quite tricky and interesting question. So just as an outline for this talk, first I'm going to talk about how we can integrate human and AI predictions, which are aligned in a prior-free setting, and I'll motivate why that matters. And I'm going to start with a baseline of agreement, and then talk about how this agreement actually is a great way to get at not just agreeing on things, but agreeing on something that's correct. And then part two, if I have time, is I'm going to talk about, well, what if they're not aligned? How can competition between AI providers help with that? Um, and I'm going to say that there are, in fact, conditions under which competition between different AI providers can lead to aligned outcomes, even if the AI providers aren't aligned themselves. Great. Okay, so part one, integrating human and AI predictions. The high level ideas here is we're going to design some protocols for interaction between human and AI systems, which are based on well-studied Bayesian agreement protocols in the Bayesian setting, but we're going to relax a lot of these Bayesian assumptions so that it becomes more reasonable for the human AI setting we're considering. Okay, back to our motivating example. Let's say that there's some operation that the doctor wants to perform, and they think, okay, maybe this is a good idea for this patient. And they ask the AI what they think the risk of the operation is. And the AI comes back and says, I think it's 20%. Now watch the doctor's face here. This is important. Look at this. Oh, she got sad. Yeah. So the doctor's sad. Why is the doctor sad? The doctor disagrees. The doctor has some instinct herself about what she thinks the risk is, and she thinks it's something different. So what do we want to do with this scenario? what might we desire going from this interaction, right? Well, we might first desire agreement, right? There's already some natural tension which relates something to trustworthy AI, which is if the doctor doesn't ever agree with the AI system, then she's either going to not use it or she's going to use it, but she's not going to feel good about the results. And so it would really be nice if they could reach consensus. Um, and also, maybe more directly measurable, we would like to have accuracy. We would like it to be that the decision that they agree upon or whatever decision they made is good. And I think there's two natural benchmarks within accuracy you could consider. The first is no harm. This is the lower benchmark, which just says, okay, well, maybe it's not perfectly accurate, but whatever decision was made, it's as good as the best of either party alone, right? So it's not like I had some decision and then I used some protocol that you gave me, and now the outcome is worse than if I hadn't used it. The second is a higher benchmark, the highest possible that you could reasonably get, which is information aggregation, which says, okay, the resulting decision is as good as if they both had just taken the private information they had and completely clumped it together, and they made an optimal decision based on that information. Okay. And I'll talk a little bit more about why the protocol can't just be we're going to clump the information together. Because, of course, that would achieve information aggregation. So, in the Bayesian setting, um, agreement protocols are something that's been studied. The idea being that, so what do I mean by the Bayesian setting here? You have some state of the world, and there's a shared prior over that state. So, for example, the state could be um, the efficacy of this particular treatment, the danger of this operation. And then you have two or more agents, and they have some variable. So you have like some state of the world X, and they each have some variable state of the world Y. They each have some variable X, which is correlated with the state of the label, which they get revealed to them. So this first agent doesn't know what the second agent's information was, but they all know the joint distribution over these private pieces of information in the state of nature. So she has some prior over it. And so now, the question is, how can they, with getting potentially different hidden signals about the state, how can they actually reach agreement about what the state is? So it turns out that if they just exchange their expectation back and forth, um, when they see the new piece of information from the other person, they update their posterior based on it. Then, if you're in a one-dimensional prediction setting, then quite quickly you will reach agreement. And here I'm talking about epsilon delta agreement. Epsilon is, well, if you're agreeing on the expectation of something and you're within epsilon, I'm counting it. That's good enough. And the delta is saying you're getting it with probability 1 minus delta over the draw from the original shared prior. So this is the original agreement framework. Um, and by the way, the agreed upon prediction is going to be already weakly more accurate than either initial predictions. Why is that true? Well, all we're doing is exchanging information. Like you're only learning more. Okay, so why, first of all, is agreement a promising framework? So it is tractable. Um, in Bayesian settings, if you're interacting over rounds, then you only have a polynomial number of rounds before you lead to quick consensus. And it requires only sharing predictions. So why does this matter? So what would it mean for an AI system to share all of its hidden information with a human? It would probably mean sharing all of the model weights. And there's kind of two problems here. The first is that it's just a huge amount of information. And the second one is even if it wasn't somehow, it's not something that is legible to a human. And finally, as mentioned before, this is at least weakly accuracy improving. So we already have this do no harm condition because all that we're doing is revealing information. Okay, so far so good. But why is this not, why are we not done? So as I've alluded to, Bayesian rationality is a quite strong condition. So what it requires is that you have a agent who has information And every time they get new information, they do a completely optimal update of their posterior using Bayes' rule. And humans and AI models don't necessarily behave like this. Um, like in particular, this can be an intractable operation if the state space is complex, which in the real world it is. So unless we are willing to assume that humans, are always able to do computationally hard problems, then I think it's hard to assume that this is always the case. And AI models also, I think thinking of them as Bayesian rationals is pretty unnatural, because of course they are not even based in the same sorts of fundamental operations that humans are, which is why we came up with these notions of rationality. Furthermore, the common prior is the other fundamental element of the Bayesian framework, which is that there's some core understanding that all the agents have at the start about the general state of the world. Um, Again, human and AI models are very different, right? So we're not just imagining a interaction between two different agents who are kind of from the same place. In some ways, this is as far away as you can get. These are two different types of agents. And so I think it becomes increasingly untenable to imagine that they have a common prior. So we would like to be able to relax these assumptions while still guaranteeing fast agreement. By the way, I don't know if there are any questions. I know that you're supposed to put them in the chat, but I don't know if I can see the chat. So hopefully, someone can let me know if there's questions because I'm happy to answer questions at any time. Okay, so anyway, the answer is can we relax them? The answer is yes, we can relax them in a repeated setting. Okay, main results are I gave this motivating example, but often the same human AI pair will make many decisions together. So lots of patients would come in. So in this setting, we can remove the assumption of a shared prior. We're introducing a new notion of calibration called conversation calibration. And this is something that's satisfied by Bayesian agents, but it's strictly weaker. And it's efficiently enforceable on an AI model without losing any accuracy. And if all the agents satisfy conversation calibration, then they quickly reach agreement. And there's also a weak notion of accuracy. You have the a do no harm condition. Um, and I will then talk about how this is relevant for information aggregation. So before I move on, let me explain what calibration is. Some of you may know, some of you might not. So imagine that you are a weather predictor. You're predicting the weather, and you say that there's a 70% chance it's going to rain tomorrow. And then tomorrow comes, and it does indeed rain. So now we can ask, did you do a good job? Was that a good prediction? Well, it's a little hard to tell, right? I mean, it just rained once, right? And so, you know, maybe it was actually always going to rain that day. Maybe it was a flash flood warning for weeks. And the fact that you said 70% is just a weird hedge and it was really much closer to 100%. Or maybe it was very strange and unlikely it was going to rain that day. And so the fact that it rained, you just got quite lucky. It's like very hard to reason about these things in a one-shot environment, right? But luckily, you're a weather predictor. So there's lots of days that we can evaluate you over many days. And now we could say, okay, um, all the times you said 70% chance of rain, we could look at those times and we can ask, did it rain about 70% of the time? And this is the idea of calibration, which is that you're not just unbiased over a sequence, but on the level sets of your predictions, conditional on the times that you say a certain percentage, you want to be unbiased on those. So here looks good. It rains about 70% of the time you say 70%. But we would also look at all the other level sets. So we can look at 20%. This doesn't look so good. So actually, on the days you said 20% chance of rain, it rained a lot more than that. So this suggests, this is sort of a smoking gun, that you're not actually predicting in a you're missing some information about the way the world works, right? So this is the idea of calibration. And sort of formally, the definition is that you look at all your level sets, and then all those level sets, you take your bias. And maybe you do like an L2 error, you could do L1. There's lots of different ways to do it, but that's kind of the core part. Okay. Um, Now we can move into our sequential agreement protocol armed with that notion of calibration. So Recall before we talked about this idea of a patient coming in. So now, we'll have different days, and every day we'll have a new patient coming in. So on the first day, a patient comes in, and I talked about these features. Some were legible to the human, some the AI system. And I'm going to talk about those as being XH and XM, with this T representing the day that we're at. So on this first day, um, our human and the AI model are going to have a conversation. And as inspired by the Bayesian Agreement Protocols, when I say conversation, I mean they are going to exchange some statistic back and forth. What the statistic is about the risk of the operation in this case. And notice I haven't yet told you how they're doing this. The answer is it's going to satisfy this thing called conversation calibration, but I really need to define the transcript before I can tell you that. So bear with me. So in some way, they are doing this exchange. And then at some point, hopefully, they'll get within epsilon of each other. And then the conversation will terminate and they will have agreed. Then the state of the world will be revealed. Then the next day, a different patient comes in with potentially different features. And again, they will have a conversation in the same way. Um, and it might terminate at a different time, right? We're not controlling exactly the length, only hoping that we can prove that it won't last that long. And so on for T different rounds. So that's the transcript of play we're looking at, right? Notice it's two-dimensional, but one of the dimensions is time. It varies. And we're going to talk about the different patients as happening each on one day. So days are going left to right. And then up to down are the rounds of the conversation. So rounds are going up to down. And I'll try to keep that straight in this presentation. Wonderful. Okay. So now that I've defined the transcript, I can now define what conversation calibration means on this transcript. So recalling, normal calibration says that predictions are unbiased on subsequences defined by your prediction. Conversation calibration. Now, of course, we have this multi-dimensional transcript. So in order to even make it make sense a little, we want to make it's going to be an operation that occurs on every single round. Like there's basically like if you look at like all the days that are happening on a particular round, um, so like if you look at like all of like this green line, this orange line, that's what this is going to operate on. So basically on all predictions in each round, they're unbiased, not just on subsequences divided by your prediction, but also on that joint with the prediction of the other agent in the previous round. But just the one previous round, not all the previous rounds. And this is important. And I'll talk about that more concretely. I'll give an example with this picture. Okay. So conversation calibration. Let's fix this particular round. So say this is round two. And let's say that this is the AI model. This is their round. So let's look at what conversation calibration means. So you would look at, for example, all the days in which the model predicts something that's close to 0.1. And then you would look at the intersection with all the days that in the round before the human predicted something close to, say, 0.2. So that intersection are these 3 days. So now you would say on these 3 days, it needs to be that the average is around 0.1. We need to be unbiased with respect to those days. Now, we can also look at the intersection of this 0.1 at round two with all the times that the human predicted something close to 0.5 the round before. So here that would be just as one day. Though of course, this only all makes sense if you have lots of different days. I have a small example here. And so now again, on this subsequence, the average would need to be 0.1 as well. So that's conversation calibration. And writing it formally, at least if you have a conversation calibration of 0, you can say that a model satisfies conversation calibration. Basically, what we have here is we're saying that if you look over all the days, and then you just look at a particular round, then let's look at just the days that satisfy the prediction of the model being something, and then the prediction of the human in the previous round being something. Well, on that, the bias should be zero. And you need this to be true for all the rounds and all possible, interactions of different prediction pairs like this. Any questions about the definition of conversation calibration? Okay. So informally, the result is that if both the human and the AI have this conversation calibration condition, then on a 1 minus delta fraction of days in this protocol, they're going to reach agreement with an epsilon and at most 1 over epsilon squared delta rounds. And this is true even in adversarial online conditions when we don't have a shared prior. Okay, what's the intuition? The intuition is that disagreement is going to decrease squared error if your conversation calibrated. And you can only decrease it so much. So we can use it as a potential function that gets us to agreement. Here's a quick proof sketch. So let's look at just a subsequence of days that make it to round K, where the model sends over a prediction of 0.2. So here we go, we're at round K. The model is sending 0.2. And now we can ask about what's going to happen in the next round. So in round K plus 1, there's two things that could happen. The first one is that in most of those rounds, there is agreement. Okay, that's good, right? What we're trying to show is that agreement happens quickly. So this is a good case. If every time we go to the next round, we divide by 2 the number of disagreement rounds, then that's nice. We have like a log distance of disagreement. That's perfect. Case 2 is that's not true. And in fact, in more than half of those rounds, there is disagreement after in round K plus 1. Okay, so what does that mean? Well, because we defined agreement as being epsilon agreement, that means that in at least half of the rounds at K plus 1, the human must be predicting something that is at least epsilon away from 0.2. Excuse me. Okay, so turns out we can use this to say that a human must have substantially lower squared error. So why is that true? So remember that the predictions around K plus 1 are conversation calibrated. So precisely what that means is that if you look at the intersection of when they predict something and when the person of the round before predicts something, it should be unbiased. And in fact, like that's exactly what we're getting in this case. We're looking at all the times that in the round before 0.2 is predicted. And then in this round, actually a couple different things could be predicted. And so you have a calibration condition here. All the times that zero point 0.1 was predicted here and 0.2 was predicted here, the average should be 0.1. So what that means is that according to this subsequence at round K plus 1, it's a calibrated subsequence. So here's a nice fact about calibrated subsequences. Any sequence that's calibrated, but if it's not a constant predictor, it has lower squared error than any constant predictor. So why is that true? So like imagine that I have a sequence which half the time is 1 and half the time is 0. So the constant predictor will just say 1/2 for everything in the sequence. And that will be calibrated. But there's lots of other ways to be calibrated, right? You could exactly get every time it's 1 and every time it's 0. You could like 2/3 of the time on something which is mostly ones, say that it's 3/4, and the other time say it's 1/4, or some math like that. And the idea being, right, that anything that you do, which is also calibrated but has more refined level sets than just predicting the same thing all the time, is actually going to always be more accurate. So what that means is if you are calibrated around K plus 1, then if you're not agreeing most of the time with round K, it must be because you are actually doing something smarter and you're doing something that's decreasing the squared error. And both the human and the model are conversation calibrated. So I can apply this argument to every round from K to K plus 1 and say that if we're still disagreeing, it must be the squared error is going down and down. So putting this all together, squared error can't go below 0. So you can look at the max possible squared error And then we can divide this by the decrease in squared error whenever you have a substantial amount of disagreement. And basically what you get is that it's about 1 over epsilon squared delta, where you have this beta t term that has to do with some calibration parameters, and it goes to 0 as t gets large. Recall t is the number of days of this interaction. And, we're only decreasing error. And by the way, why do we care about this thing called conversation calibration? Well, it's actually much, much more tractable than Bayesian updating. This is actually something that even against our arbitrary adversarial online sequences of losses, where you could think of that as an adversary gets to choose what the outcome of the particular operation is, you can still get this with sublinear bounds. So in particular, here we can see that this beta becomes t to the negative 1/3. Right. So as I was mentioning, conversation calibration is just a much weaker condition than Bayesian rationality. So for those of you who are familiar with generally how calibration works, you can take any sort of online sequence of decision processes, and you can then turn it into one that's calibrated. And you can do it in a way which, up to asymptotic terms in t, doesn't decrease its accuracy loss. And you can do that here too. Basically, the first prediction in each conversation is going to be from this base model, and then we can apply well-known algorithms with calibration guarantees for later rounds, and that will do what we need. It's also satisfied by Bayesian updaters. So, for those who are happy with the Bayesian model, the Bayesian model still applies. This is a strictly weaker generalization. So this is also a more flexible framework for humans. If you imagine humans are Bayesian, well, now they can be Bayesian plus something else, and it still works. Apologies for the cough. I was sick last week, and so I have this lingering cough. Great. Okay, so now we can ask, okay, is agreement enough though? Because now we've talked all about agreement, but are we as best as we could have done if we saw all the features? And the answer is certainly not always. When can we guarantee this notion of information aggregation without sharing features? Okay, so I'm not going to go into as much detail about this follow-up work, but I want to give some high-level intuition. Um, so recall that we just showed that if both agents are conversation calibrated, then the protocol is going to lead them to agree on a set of predictions. So if they have a stronger notion as well of no swap regret with respect to their function class, which I won't define fully for those who don't know, but basically this is just saying, what if both of their sides also had some predictions which gave some guarantee with respect to a function class of predictions? Then these agreed upon predictions would have no regret with respect to both function classes. They would get some joint guarantee on both of the function classes. Because in the end, the thing you're agreeing upon should be the same, right? So we're kind of combining these guarantees that we have separately for the joint predictions. So then the question becomes, when is that enough for information aggregation? This notion of no regret with respect to both function classes jointly. And we give a weak learnability condition that characterizes when it's enough. So yeah, I'm just going to do a very high level perspective on that. But just so you know, we also have things to say about actual accuracy. Wonderful. So for the last 10, 12 minutes of this talk, I'm going to go to a slightly different setting. And so I'll just give a taste of what's happening here, which is to say, talk about alignment. So great, conversation calibration. It's quite easy to satisfy on a model if it wants to satisfy it. But it's also really easy to violate without a human noticing. So you can imagine the human asking a question, what medication should I prescribe to this patient? And maybe the AI model is funded by the healthcare company Johnson and Johnson. And in fact, the data itself suggests that the Johnson and Johnson medication is less effective than the Pfizer for patients like this. Nevertheless, because of the training decisions that were made by the company, the model recommends prescribing Johnson and Johnson for this patient. And maybe the human actually agrees with this because based on everything they know, this seems fine. But it turns out that there was information in the patient data that the AI model had, which would have suggested that Pfizer would have been better for this patient. And the human is not able, and the patient are not able to benefit from this information because the way the AI model was trained, it wasn't effectively using that information because it didn't have the same incentives as the doctor and the patient. But we can then ask, what if there's also a Pfizer LLM available on the market? Can this help? And we're not promising that the company Pfizer is aligned with patients. They can be just as misaligned as J&J, but misaligned differently. We can then ask, might competitive forces help align the market for LLMs, even if individual actors remain misaligned? So the upshot here is we're going to model LLM training in competitive markets as a multi-sender Bayesian persuasion game. And we have this assumption called market alignment, which is weaker than this general notion of full alignment, which still leads to good outcomes for a downstream user. Before I move on, a quick note on alignment, because this is a big word. A lot of people use it in different ways. The way I see it, there's two really important sources of misalignment between an AI system and its users, because that's the core way I'm defining alignment, which is you have an AI system, it's doing things that the users don't want it to do. One is a failure of an AI company to properly encode their goals into the AI model. So the company wants to do good things for the users, but there's this hard technical problem of making AI systems operate the way you want them to operate. The second is the success, at least to some extent, of an AI company to encode their goals. But the company's goals are misaligned with the user's goals. Both of these are real and important problems. And in this talk, when we talk about alignment, misalignment, we're really focusing on the second one. We're thinking about the incentive problem as opposed to the technical problem. So, what does it mean to have multiple AI providers in this setting? We're going to model these now I want to use the word model in two different ways. We want to think about the models that these AI companies train and deploy as being conversation rules. So there's some information they have, right? You can imagine, their training data. And what they're doing is they're mapping it um, to a way of conversing with a downstream human. So there's some conversation they're having. There's a conversation prefix. And what XB does, this hidden information of the model, is it maps it to the next message. Um, and a doctor gets to play with all the deployed models and then, get a sense of the types of problems that she cares about, the way that they answer it, and then chooses to subscribe to her favorite. So the one that's the best at advancing her objectives. And then when she actually uses the models, she's going to use one, her favorite. She gets to see her own information about that because, of course, humans also have expertise, as we've established so far. And she's going to then have a conversation with this model she's subscribed to. And at the end, she's going to take an action. And training AI models is quite expensive, right? So we're thinking about this as a commitment to the model they deploy. Knowing that the human user is going to, make this decision in a way that tries to optimize for who she thinks is the best AI to interact with, and then she's going to make a decision based on what she's learned, a decision that the companies have preferences over, perhaps. The companies are going to strategize against one another to advance their goals. So we're thinking about this as a multi-agent Bayesian persuasion game. For those of you who aren't familiar with Bayesian persuasion, the general idea is you have some state of the world and you have some sender, in this case, senders, and you have a receiver. And the senders have to commit to some sort of a signaling scheme which maps from the true state to a message. And it has to be like a legitimate device, right? It can't be lying, but you can commit to something in such a way where if you have incentives about the kinds of beliefs and downstream action that the receiver has, you can only give them information in ways that help you and leave it kind of fuzzy if you don't want them to learn something that would help them do something you don't want them to do. So that's the general idea. And that's something that we're bringing here to this AI training setting. So in this motivated example, the action set of Alice is, say, the medications that she could prescribe to her patient. The state of nature is, for example, the possible efficacies of all of the different medications for this patient. And Alice, the doctor, I'm also calling her Alice because in Bayesian persuasion, generally you have the senders are Bob and the receivers are Alice. Alice has some utility, which is depending on this action, this state of nature. So, hopefully high if it's an effective medicine that she chose for the patient. But the Bobs, the companies, also have utilities. And maybe in some ways these utilities are aligned, probably even just for reputational reasons going forward, they would like to be pretty good at helping this downstream person, but they might be misaligned in other ways. So, for example, one of them might have a strong preference for the action that the doctor takes being to prescribe J&J, for example. Alice has some secret information, whatever expertise she has on the question that she's asking. And the Bobs also have some secret information. And importantly, in this model, all the Bobs have the same secret information. We're motivating this by kind of saying that all of the different Bobs are, all the large AI companies are essentially training on the whole internet. And so this secret information is that data. But it would be really interesting to see what happens if all the XPs aren't the same. That would be a really interesting next step. So the general interaction goes like this. There's some shared prior. By the way, I will just add in a little asterisk here. Um, Eagle-eyed people might be confused why I poo-pooed the Bayesian setting in the first part of this talk, and I'm now fully in the Bayesian setting. And that's entirely fair. So the general way I see it is you have to solve the Bayesian setting first. So for the first part of this talk, the Bayesian setting was solved, so we solved the non-Bayesian setting. And this part of the talk, the Bayesian setting wasn't solved, so we're solving that first. But it'd be really great to think about what it looks like to take the Bayesian setting away in the second part of the talk as well. So all the parties know the shared prior, and each Bob is going to select a conversation rule, which maps from this hidden information and a conversation prefix to some continuation of the conversation, right? Because of course, the way that people interact with AI systems is they usually don't just ask one question, they engage in a conversation to try to get more information. And that's something that's captured in our model. So Alice, given this conversation and her own observations, can form a posterior belief over the outcomes. And then she can take her utility maximizing action. Um, and she's going to choose the conversation rule that maximizes her expected utility. And when we talk about these joint distributions over states and actions, we're going to write this as like I star thing here. And note that this joint distribution is enough to determine Alice's utility and also all the utilities of the Bobs. And then Alice is going to choose the provider, after some experimentation, which gives her maximum expected utility over these deployed models. And at deployment, we can then ask how well she does. We're going to sample this a problem instance for the prior. The conversation between Alice and this Bob are going to be induced. And Alice is going to hopefully learn something from the conversation. Because, why is she learning something? Because the conversation rule of that Bob is potentially correlated with their hidden information, right? And that hidden information is correlated with the state that she cares about. So this is just the mathematical foundations for just saying, it should be that when she asks an AI model about a question she cares about, she should learn something about it. Okay. So there's some prior, there's some particular conversation rules that I committed to. I don't know why this one is flipped. But all of these, the doctor gets some sense about what this outcome might look like for her. She picks one to subscribe to, and then they actually have some conversation about what's going on for this particular problem she has. She interacts with it in some optimal way, in order to extract the information she needs. And then she computes her posterior and takes the optimal action. So the upshot is that what I've just described is a game between the bobs, where their actions are conversation rules. And you can then ask, what are the Nash equilibria of this game? Now, I'm almost out of time, so I won't go through the proof sketch, but I will try to just tell you the upshot of what's happening here. So traditional alignment is, in this setting, I think would be if there's a particular AI company whose utility is exactly the same as Alice's, right? So for any combination of action and state, the company is exactly as happy as the downstream user is. That would be nice, right? But I think it's pretty unreasonable to expect. Um, but if that did happen, then the utility that Alice would get, we're going to call it opt. If one of the companies was just trying their very best to give Alice as helpful information as possible, we can call that opt. So our work says you don't need that. Instead, all you need is this weaker notion called market alignment. And if you have this, then all Nash of this game I've just described are going to lead to good outcomes for Alice. And what is a good outcome? A good outcome is that she gets at least opt, this thing I just defined. So what is market alignment? Market alignment says that Alice's utility can be written as a non-negative linear combination of the utilities of the bobs. So let's just take a look at what that might look like. So if you had, say, a finite number of uh, actions and a finite number of states, then you can very concretely think about some particular AI company's utilities being a point in some high dimensional space. And you can think about that for a bunch of these different companies, right? And now you can imagine maybe this is Alice's utility. And it's not that near any of the utilities of these companies, but it's in the convex hull, which is a special case of being a non-negative linear combination. So this is great. It turns out that this satisfies market alignment. The last thing I'll do here in this talk is just show you formally, so we have no confusion about what market alignment is. So you have utilities of these different bobs, and there just need to exist coefficients such that you can write the utility of Alice by taking these utilities of all the bobs and multiplying them by these coefficients, and you can even add some constant at the end. So what this means is maybe every AI provider is substantially misaligned, but collectively their interests span Alice's. And one nice example of this is that that Pfizer and J&J example, where maybe each of them is misaligned, but they're misaligned in exactly opposite ways, right? Maybe one of them prefers J&J being prescribed over Pfizer, one prefers Pfizer over J&J. And so market alignment is going to apply here because in the linear combination of just these two models is Alice, because these are the only biases they have in the simplified model. And so the theorem says if all the bobs satisfy market alignment together relative to Alice, then in every single Nash of this game, not just one, every single Nash, Alice gets utility at least that of opt, i.e., the benefit she would get by interacting with a single perfectly aligned bob. And I am out of time, I believe, so I will not go through the proof sketch, but I will open up the floor for questions, and thank you all so much for your time.